All right. So yesterday we saw in the first lecture. I mean, we just saw the Boltzmann equation, the relativistic version of the Boltzmann equation, which I'm going to write down so you remember. And so today comes we are going to start with the applications. So so first of all, I will show you how the relativistic version of Boltzmann's H theorem works. So that's pretty much the same as in the Newtonian setting. And then we're going to talk about equilibrium solutions. So those are the ones that are distinguished by having non-zero entropy production. And we're going to see that in the GR setting, this puts very strong conditions. Okay, and then we're going to talk about perturbative expansions. So the Hilbert expansion, where you expand the distribution function around local equilibrium. Talk a little bit of the Chapman-Enskog method, and if we have time, we will derive the first order fluid theory, which is a truncation of this perturbative expansion to the first, after the first order correction term. So that would correspond more or less what you do for Navier-Stokes in the Newtonians in the non-relativistic setting. All right, so recall from yesterday. So the Boltzmann equation had this form. So there was the transport term, which is described by the Liouville vector field. F is the one particle distribution function, which is a function on the future mass shell. And then there was this collision term, which is this quadratic integral operator, which I explained yesterday, which depends on the differential cross section. So which describes the nature of your binary interaction. And then recall also that we had this integral form of the Boltzmann equation. So we multiplied the Boltzmann equation with a test function psi and integrate over p, and then we had this integral form of the equation. And the right hand side was 0 if psi was a collision invariant. So if it was constant, either constant or a component, say, of the form moment. And then the last thing I would like to recall is that we had this observable, so this symmetric tensor fields that you obtain by integrating the distribution function over different p's. And then the divergence of those, so basically the divergence you can put below the integral formally, and then this becomes a Liouville vector field. And if you combine this with the integral form of the Boltzmann equation for collision invariance, then you get the balance laws out of it. Okay, so you have J mu, which is this tensor field for S equal 1. And you have T mu nu, which is a stress energy tensor, which is the case S equal 2 here. And those two are divergence free. I mean, if F satisfies the Boltzmann equation. Now, let's come to the H theorem. So for the H theorem, what you do, you choose psi not a collision invariant, but 1 plus log F. So A here is just a positive constant that, I mean, for physical reasons, you put it because F is not dimensionless. But if you don't, you can just think of A equal 1. And now, if you apply again this divergence identity, this proposition about the divergence, and you combine this with the integral form, then you get what you get is this equation here. So you have the divergence of a covector field S mu is given by this expression here. And this covector field S mu is the integral of F log F. Okay, and you put here minus KB. KB is Boltzmann constant, and this is the entropy. This is the Boltzmann entropy, is what it is called. And now you see the interesting thing is that what you get under the integral here is positive definite because it has the form I mean, this is log y minus log x, and this is y minus x. So this is always because the logarithm is monotonically increasing. So this is always positive, except when x is equal to y. Okay, so the first, so this has an important implication. So for example, if your space-time, you assume a space-time now to be globally hyperbolic, and you assume also that the distribution function somehow decays sufficiently fast at infinity, then you obtain the second law of thermodynamics. So you integrate this over a space-time region between two Cauchy surfaces, say, and then you define. I mean, if nu here, nu is the normal to the Cauchy surface. So you define this would be the entropy contained on the Cauchy surface, if you want. So if this Cauchy surface C2 is the future of C1, then this S of C2 would be larger, equal than S of C1. Okay, so you have a non-decreasing entropy. Okay, so that's the first consequence of this theorem. And then you can ask, well, when is this zero? So sorry. So when is there no entropy production? So when is this exactly zero? And as I said, is when x is equal y, or in other words, if f1, f2. So that's remember this notation. This is f evaluated p1 and f evaluated p2 before the collision, and this is a product of the f's after the collision. Okay, and that means if you take a logarithm on both sides, that means that the logarithm of f is a collision invariant. But we had this exercise yesterday, which said any collision invariant is like of the form alpha plus beta mu p mu. So log f has to be this form, and if you take the exponential again, that means that f must have this particular form. Okay, and this is known. So f must be alpha, some function alpha, e to the beta mu p mu. So where beta is a vector field. Okay, and this is known as the Hüttner distribution function. So these are the states that are characterized by zero entropy production. I copied this here again in this slide. Okay, and of course alpha must be positive and beta must be future time-like directed. Otherwise, you cannot compute the observables. Now, let's see what the observables are for this particular distribution function. So if you want, this is a relativistic generalization of the Maxwell-Boltzmann distribution function in a non-relativistic case. And you can compute this in a nice way by, through these tricks from statistical mechanics. So you define a generating function, which is just the integral over P of the distribution function over the future mass shell. And then you see if you take partial derivatives with respect to beta, then this will give you this S tensor. So you take S derivatives of beta. And then, so you just need to compute Z, and then everything follows. And to compute this integral, so you can exploit the Lorentz invariance and then say you choose an orthogonal frame which is aligned with beta, where the time-like leg is aligned with beta. So E0, E node, E1, E2, and E3. This is an orthogonal frame of vector fields or covector fields here. And then you expand P. You can parameterize in terms of a hyperbolic angle, and N would be on S2. It would be normalized to 1. Okay, and then you plug this into this integral, and you use spherical coordinates and so on. And then what you can express this Z in terms. So what appears here is the modified Bessel function of the second kind. So this is given by these integrals here. So these are tabulated functions. And this z, this generating function has in this form. You can compute it explicitly in terms of this function, this special function. So little z here, so that's m times the norm of beta. Okay, and now you just take partial derivatives and you compute now the current density. So the current density you can always write as a 4 vector, which is normalized, the time-like, and the quantity n, which you call n, so this is the particle density. And if you write down T mu nu, then you will find it has a UU component and then a G component proportional to G mu nu. So that's the pressure, and H here, that's the enthalpy per particle. And then you can compute this explicitly. So N, for example, is given by, again, by this, in terms of this Bessel function, modified Bessel function. So here the 4 velocity would just be this vector field beta mu normalized. And this is the expression for the enthalpy and the pressure. And what this describes to you, so this is just a form of a perfect fluid in general relativity. This has exactly the same form. So, and furthermore, if I divide the pressure by the particle density, then you get m over z from these expressions, and this you can identify with kb times the temperature. So that, and that means that the temperature is given by these expressions. That's 1 over kb times the norm of beta. So you can look at what happens if the temperature is very low. So low temperature means large z. So the temperature goes like 1 over z. So if z goes to infinity, you can expand, you can just expand this quantity. And then you will find that the enthalpy is the mass of the, I mean, this is the enthalpy per particle. So this is the mass per particle plus 5 half kBt. So these are like the Newtonian expressions that you find in any book on just a simple gas. and this 15 over 8 kBt squared over m, this would be the first GR correction. Well, not GR, the first relativistic correction. And you can also look at the ultra-relativistic limit. So when the temperature is very high, and then H goes like 4 kBt. Now, you can further reinforce the interpretation of the temperature by looking at the entropy. So these are just standard arguments from, say, thermodynamics or statistical physics. So if you, because we're an expression for the entropy flux or the entropy current, then you can just compute it and you will find it is proportional to the, for this Newton distribution, it is proportional to J mu. And this proportionality factor would be the entropy per particle, which you can compute explicitly. And now the nice thing is that if you vary, I mean, this class of Newton distribution functions, you vary alpha and beta, then you will find that this equation is satisfied. So TdS would be dH minus dP over n. So these are variations just within this Newton distribution model. And this is the first law of thermodynamics. So this reinforces that this T really describes the temperature in this case. Okay, now, so remember this distribution function came from the requirement of having 0 entropy. But if you want to take this as a solution of your Boltzmann equation, so 0 entropy production means that the collision term is 0. But then remember the form of the Boltzmann equation. So if the right-hand side is 0, the left-hand side should be 0 as well. So we have to look at the transport part. So, and if you plug in this equation into the transport part, so now you have to check if LF is equal to 0. And now if you divide by F, you look at L of log F, then you get this expression here. And this, of course, this should be zero, but zero on the mass shell. So that means it should be zero not only for all x, but also for all p's on the future mass hyperboloid. Okay, and this is a very strong condition because you see, so you can show that it will tell you that log alpha is constant, and that the symmetric part of nabla mu beta nu should be zero. So in other words, what it tells you that this is a solution only if beta is a time-like killing vector field. Okay, and alpha is constant. Okay, so but this is of course very strong because it means that your space-time, for this to work, your space-time should be globally stationary. So it should have a global time-like killing vector field. And of course, this rules out many interesting examples. So for example, it rules out typical equilibrium space-times like black holes, like Schwarzschild, Kerr, and so on. But also cosmological space-time like Friedmann, Lemaitre, and Walker, because they don't have a globally defined stationary, a global time-like killing vector field. Okay, so the summary so far says also if space-time is globally stationary, then there are preferred solutions of the Boltzmann equations, which are characterized by this zero entropy production and are interpreted as global thermal equilibrium states. And these states are described by the Hüttner distribution function, which I wrote again here with explicit expression for alpha in terms of the particle density and the inverse temperature. And beta mu is u mu over kVt. Okay, so this is. And now as an exercise, you can check that if you have this solution, then basically this comes from the requirement that alpha is constant and beta mu is a killing vector field. So you can check that the temperature and the particle density, they should be constant in time. So it means constant along the killing vector field or along derivatives of u, which is the same. However, they are not necessarily constant in space. So if you compute now the derivative of t, so this capital D, that refers to the derivative of n along the direction orthogonal to u. So this delta is an orthogonal projector, the projector orthogonal to u. Okay, and if you compute those derivatives, they are not necessarily zero. So for example, the acceleration of u is tied to minus the gradient of t over t, special gradient of t over t. And this is again related to the gradient of n over n. Okay, so if your space-time is static, for example, but not Minkowski, then the accelerations and the temperature doesn't have to be constant in space. Okay, and that's known as a Tollmann-Ehrenfest effect. Okay, but now what if you want to look at the space-time which is not globally stationary, like you're going to do cosmology or something like this? Can one still talk about thermal equilibrium? And this is where now local equilibrium will come in. So the intuition here is that one should still expect to have some at least approximate thermal equilibrium states, provided that the collisions are sufficiently important. So sufficiently important, that means that somehow the collision term dominates over the transport term. Okay, so if this is the case, you could still hope to have approximate, equilibrium solutions. Okay, now to make this more precise, we are going to use a scaling argument. So we are going to introduce these two length scales. So these are not precise definitions, but it's more to define this rescaling. So we are going to assume that there is like a macroscopic length scale. So this is more or less a length scale over which, like the macroscopic quantities, vary. So you can define it, for example, by taking the particle density, which you can define in this way. So this is just a norm of J mu. And you divide by the square root of its spatial gradient. Okay, so that would define you a length scale. And then you introduce the mean free path. So the mean free path is intuitively, it's the mean distance between collisions. And you could define it in a formal way in this way. So this is just the length which makes the product of the total cross section times L times N equal to 1. Okay, and so this is a length scale. And then you introduce a Knudsen number, which is the ratio between these two length scales. Okay, now the idea of having of the collision term dominated, that's going to be reflected in the assumption that the mean free path is much shorter than the macroscopic length scale. So in other words, this Knudsen number is going to be very small. Okay, and this is what is going to be called the hydrodynamic limit. So the hydrodynamic limit will be the limit where this Knudsen number is very small. Or in other words, the mean free path is much smaller than the macroscopic length scale. Okay, so to do the scaling arguments, and what you do, you rescale your variables in the Boltzmann equation. So x mu you rescale with the macroscopic length scale. So x bar would be dimensionless, the rescale variables. So p mu you just rescale by the mass. The distribution function you rescale in this way. So this is basically a dimension analysis argument. And then this differential cross section has the dimensions of L squared. So this, but it should go like 1 over the mean free path. So you rescale it this way. And if you do all this in the, you get what is called the rescaled Boltzmann equation. Okay, so all these quantities with a bar, they are now written in terms of these dimensionless coordinates. And what you get here in front is epsilon, which is a Knudsen number. Okay, so you get now this rescaled equation. And what we are going to look is like at solution, which where you have a, which you can, I mean, which have an expansion epsilon. So more precisely, so to 0th order in epsilon, you see if epsilon is strictly 0, then you recover exactly what you want, that the collision term is 0. And that implies that the distribution function now should be the Hüttner distribution function. So that's what I just showed you before. But there is one important difference, is that now there is no left-hand side. So the left-hand side, so this epsilon now is, so this is 0. So now there is no restriction on alpha and beta. So alpha doesn't have to be constant, and beta doesn't have to be a time like killing vector field like before. It could just be any time like future directed vector, and alpha just need to be positive. Okay, and this is what is called local equilibrium. So for global, alpha would need to be constant, and beta mu a killing vector field. But for local, this restriction now is relaxed. Okay, and then you can imagine to have formally an expansion like this. So it's called the Hilbert expansion. So you expand f in powers of epsilon. So f0 is already fixed. It is a local Hüttner distribution function. And then if you look at the first order correction, they will satisfy a linear equation for f1, which is of this form. So q was this integral operator, and now when you linearize it, then you get something like this with a source term. And then formally you can write like higher order correction. Now, what we need to do is we're going to study this linearized collision term, and we're going to define like this. So instead of working with f1, we're going to write f1 as f0 times phi. So f0 is positive, so I can write this in terms of a deviation from f0. like this, and then we divide by F0, and the -2 is just for convention. Okay, then we can rewrite this first order equation in this way. So there's this linear operator that acts on phi, and this is a source term. And now to simplify what comes next, I'm just going to drop the over bars to make it look nicer. Yes. Okay, so the first order problem then again, so we have to solve this equation here. And F0 here, so the right-hand side is given to you. So that's the log of the Hüttner distribution function, which is this collision invariant. And then we have to study then the properties of the linear operator. So this L should be the same as this L here. Okay, and for what I'm going to so this has been studied. And here, so you need to make some assumptions on the differential cross section. So the assumptions we are going to make are the following ones. So first there is a lower bound on the so here is the total cross section. By the way, this is just an integral over the differential cross section over the angles, over the scattering angle, basically. Okay, and remember G was the relative speed between the incoming or outgoing particles. So require a low bound like this and an upper bound like this. This has some physical interpretations I don't have time to explain. And then the way you analyze this integral operator, this goes back, by the way, by very old ideas by Hilbert himself. So let's write it down explicitly. So if you write it down explicitly, you have this integral here. And then you have here phi evaluated at P1 at P2 minus at evaluated P1 star, P2 star. Okay, and here's the Hüttner distribution function. Now, something you see here is that this phi1, this term depends only on P1, okay? But you don't integrate over P1 at all. So this term you can actually pull out of the integral, and then everything is known below the integral. So this first term gives rise to an integral, to a multiplicative operator. And so furthermore, it has some nice structures. So again, if we do the same trick, I mean, the same procedures before, so we multiply this equation by psi, by function psi, and by F0 and integrate, then we get this integral form here. And then again, if you use the symmetries I mentioned yesterday of the collision kernel, of the collision manifold, sorry, then you can rewrite this in this way here. And now you see that this is a symmetric in phi and psi. Okay, so this invites you to define this as to introduce a scalar product and a Hilbert space, and then you will have a nice symmetric operator. So in particular, so if you define now this scalar product here, so it's just the integral of psi times phi times F0, then it means that this operator is symmetric, I mean, formally symmetric now with respect to this scalar product. And furthermore, if you put psi equal phi here, then you see, then you get this, you get a quadratic expression. So that means this operator will be non-negative. It will be non-negative, and furthermore, you can see that the kernel is precisely when this is 0, which again, by the exercise we saw yesterday, consists of the collision invariance. Okay, and now you can formalize this a little bit more. So you introduce the Hilbert space. So you fix an event X, and then you introduce this Hilbert space, which is a L2 over the future mass shell with this weight here, and then what you do, you write the linearized collision operator. You has the following forms. It has this multiplicative operator, which is just a function nu times phi. And this new function you can compute. It is given by this integral. It depends on the differential cross section. And then you have two operators, K1 and K2. Now you can, as the next exercise, you can check that the assumption we put on nu, they imply that the image of nu is actually as a form, so that there will be a minimum which is positive, and then it goes to infinity. So it will have this form here. It will be given by this interval here. Okay, and then just some standard arguments you can then prove, because nu's are the real values. So this is a so this makes this multiplicative operator into a self-adjoint operator, and the spectrum is given by exactly the image of this. Okay, and now you treat this K1 and K2 as perturbations, and you can show that these operators K1 and K2, they are actually compact, and then you can use like tools from function analysis, like Weil's theorem, for example, to show that it won't, so this perturbation by K1 and K2, they won't change the essential spectrum. So the essential spectrum would still be equal to nu1 infinity. And from this, you can conclude that the spectrum, I mean, you can conclude this, but you can also conclude that this whole operator is self-adjoint. And then with the following spectrum, so you have 0, which is 5 times the generate. That comes from the collision invariance that you have, the 1 p mu. Okay. And then you might get some discrete eigenvalues here in the gap between 0 and nu0. Okay, but there will be a spectral gap here. And then you have the continuous part. Okay, now the important consequence for us is that now you can invert this operator if you restrict it to the orthogonal complement of the kernel of L. Okay, so the kernel of L are these collision invariants. So by restricting it to this subspace, then you basically erase this 0 eigenvalue, and then it becomes a strictly positive operator which you can invert. Okay, so the bottom line, so you can solve this equation, okay, but you need to make sure that the right-hand side is orthogonal to the kernel of L, orthogonal in this Hilbert space, and in this respect to this product, scalar product we have introduced. So explicitly, this means that if you take the scalar product of the right-hand side with a collision invariance of 1 or p mu, then this should be 0. Okay, and now there are different, so there are different ways of imposing this, as we're going to show, but this is basically the bottom line that's for the solvability of this first order equation. Yeah, so by the way, this right-hand side, if you write it down explicitly, you will have a term, I mean, it will look something like this. So these terms here, they're linear in P, and so they, or constant in P, so they belong to the kernel. And those are the terms that are quadratic in P. And we will, so what appears here, this is a shear associated to the 4 velocity. And then you have this combination here between the acceleration and the gradient of t. So remember, for global equilibrium, this was 0. This was also 0, actually. And then you have here the expansion over 3 plus t dot over t. So this will appear later in the course today, these combinations. Okay, so now let us go back to the Hilbert expansion and see if we can solve the first order equation and the next order equation maybe. So the 0th order is fixed by, I mean, we know this is a local Newton distribution function, so it has this form. The first order correction has to satisfy this equation here. And for the integrability of this equation, we need these integrals to be 0. Okay, for any collision invariance psi. Now, if you use again this divergence identity I told you about yesterday, okay, so what this means is that the divergence of the current density constructed from F0 should be 0, and the divergence of T mu nu constructed out of F0 should be 0. So in other words, the quantities NT and U that parameterize this local distribution function, they have to satisfy the relativistic continuity and Euler equations. So so here I wrote down again what these expressions are. So these are the same expressions as before. And now as an exercise, if you haven't done so yet, you can show that the relativistic continuity and Euler equations, so the balance laws that you obtain from these expressions, they are given by this free equation. So there's a continuity equation. Then there's an equation for the propagation of the energy density, or you can turn this into an evolution equation for the temperature. So CV here is the derivative of the energy per particle with respect to the temperature. And then you have the acceleration is minus the pressure of the gradient divided by NH, minus NH. Okay, so this follows directly from this form and the fact that it's divergence free. Okay, so to order 0 in this Hilbert expansion or in this Hilbert method, say this is the equation that you would need to solve. And once you have solved this equation, then you're sure that the integrability condition is satisfied. Okay, so now you can invert this operator, and you get this solution here. But again, because this solution is only inverted on the orthogonal complement of the kernel, you can add here an element of the kernel. So the solution is non-unique because it has a kernel. Okay, so you can add actually an arbitrary function phi 0 here. And this is actually needed because you can show now, if you go to the next order equation, then you can show that you will have to tune this phi 0 in order for the integrability conditions for the second order equation to be satisfied. And then the same happens at each order, okay? And what you end up with is like a hierarchy of, at higher order of linearized continuity and Viscid Euler equation, which has a source term that depends on the previous order. Okay, so these are not really the Navier-Stokes-like equation, because to order 0 you solve this, these perfect fluid equations, and then you solve order by order correction terms. So let me explain now a slightly different method of doing this expansion, which is known in the literature, the Chapman-Enskog method. And there's a subtle difference between the two, and this difference is that you don't fix, you assume that the local equilibrium distribution function F0 is constructed somehow. So more precisely, so this local distribution function, you can think of it like a 5-dimensional subspace in this infinite dimensional space of all the possible distribution functions. And now you can think of that if you are close to equilibrium, I introduce a method where I somehow project this distribution function on this set, okay? On this set of equilibrium distribution functions. And of course, there are infinitely ways of doing this. So this is not unique. And so the only restriction says that this should be in some sense smooth and reduce to the identity if you have already an equilibrium distribution function. And it turns so the different ways of doing this projection, so in this jargon of relativistic fluid dynamics, is known as a choice of frame. So choice of frame is basically how do you pick like this F0, given a distribution function which may be out of equilibrium, how do you pick NT and U, which somehow best approximates this F. Okay, and you can then study what happens if you change this choice and so on, but I have no time to go into this. So we are going to fix this choice in the following way. So now this is the new, if you want, perturbative ansatz, which looks very similar to the previous one, but with one crucial difference. And this is, by the way, something that is done in the non-relativistic setting by Laure Saint-Raymond, how she presents the Chapman-Enskog method, which I found much clearer than the physical literature. So you write so you assume you want to construct a family. It depends on epsilon of distribution functions, okay? And you write this down as a local Maxwell-Hüttner distribution function plus a correction which will be of the order of at least epsilon. So H epsilon will be like the correction term. And now you fix this F epsilon 0 by requiring what are called these matching conditions. So what you will now demand is that the first 5 moments of your distribution functions of F0, they should match the first 5 moments of the full distribution function. So in other words, that means that the integral, so the first moment will be, you just integrate over H epsilon, and this should be 0, so that the first moments of these two are equal. And then the next 4 moments is if you multiply this with P mu. So this should be also 0. Okay, so what this means is, and this is, I claim this is very natural, because this means that if you divide H epsilon by F0, this is actually the orthogonal complement of the kernel of the linearized collision operator. And this is why you can invert your collision operator. Okay, what this would mean, of course, is that this local distribution function, F epsilon 0, will depend on epsilon through n, t, and u. So that's why this depends also, I mean, it's of the order 1, but it will depend on this full, on F epsilon at the end. Now, if you look at this matching condition, like in practice, what this means is that, I mean, this condition means that the current density of F0 matches exactly the current density of the full distribution function. So this is called a particle frame. So this fixes n and the choice of n and u. And then this condition here, this means that I fix the trace of the stress energy tensor, okay? Because the stress energy tensor, if you remember, P mu, but the trace of P mu is minus m squared, which is, and m is positive, so it's a constant. So that's the same as fixing the trace. And this you can show actually fixes the temperature parameter in this local distribution function. Okay, and for these reasons, we call this a trace fixed particle frame, this particular choice. So once you have fixed that, so you plug this into the Boltzmann equation. So this is just a Boltzmann equation rewritten in this, which looks more complicated because we have separated now the 0th order term from the epsilon term. And sorry. So okay, and now you remember. So somehow we want to solve this equation. So what we'd like to do now is to invert the linearized collision operator. But to invert it, remember that the right-hand side has to be orthogonal to the kernel. Okay. So the right-hand side needs, in other words, needs to be in this space here for solvability. And now what we do is the drastic thing we do, we just replace the right-hand side by the orthogonal projection of the right-hand side. So we just project orthogonal to the kernel. Of course, you will have the feeling that now I change the Boltzmann equations, but you can show actually that the error you make, which is in the kernel, is 0 if and only if the balance equations are satisfied. Okay, so in other words, so you're allowed to make this projection if at the end you impose the balance equations. So if you impose the balance equations at the end, then this is perfectly fine. This is consistent. All right, and then if you do this inversion, then you get this expression for H epsilon. So this is an implicit equation. So you have H epsilon on the left, but also on the right. And H0 here would be the first order correction, which is given by this expression here. Okay, where this is now projected orthogonal to the kernel. So this is the difference with the Hilbert method. You didn't perform this projection, but then you would get the perfect fluid equations. Here you won't get the perfect fluid equations because you project and then invert. And then this you can try formally to solve through an expansion, order by order in epsilon. And in principle, this could be solved order by order, at least formally. Okay. So that's a Chapman-Enskog method. And then, so if you went, if you went what this gives for you, it allows you to construct from F0, it allows you to construct successively F1, F2, F3, and so on in this Chapman-Enskog approximation. Okay, but at the end, remember that this worked under the assumption that at the end you have to impose the balance equations. Okay, and this is where your fluid theory will come out. So if you now impose the balance equations, then the continuity equation will be simple because remember that J mu in the frame I've chosen coincides with J mu that you construct out of F0. So this equation just will give you just a standard continuity equation. But if you look at the divergence of T mu nu, it will have a part, a zeroth order the part, and then on the right-hand side, there will be an epsilon term, and there will be the divergence of T mu nu of the correction H epsilon. Okay, and if you write these equations down explicitly, so you decompose everything in terms parallel to U and orthogonal to U, then you get these equations here. So the left-hand side are just what you have for the perfect fluid Euler equations. But then on the right-hand side, you will have epsilon terms, which come from these correction terms here. and here appears like the expansion. So of course it's a long expression, but here, so what the only thing we did is to expand this T mu nu here in a part which is parallel to U, parallel orthogonal to U, and then there's like a pressure correction terms, and then there's this, I mean, this is basically a trace, and the trace-free part of what is called the Navier-Viscous tensor. And epsilon tilde and p tilde, they will be related by this relation due to the trace fixed condition that we have imposed. Okay, so formally these are the balance, I mean, these are the fluid equations that you get, but of course this is not yet, I mean, this is, to do that, of course, you would need to compute H epsilon to all the orders. So what we are going to do now in the last part of the course is to truncate this expansion to the first order term in epsilon. So in other words, sorry, here. So we are just going to keep this first order correction terms. I mean, it's called 0, but really it's of order epsilon because there's an epsilon in front of H epsilon. Okay, and we're going to ignore all these higher order correction terms. So that would be the equivalent what you would do in the Newtonian setting for Navier-Stokes. And yeah, this I already said. So and then what you get, so when you just compute the first order terms, then you can now compute explicitly what these correction terms are. E1. So you will have a correction to the energy per particle. You will have terms that describe the heat flux, a correction to the pressure term, and this trace-free part of the Navier-Stokes. And what you get are these expressions here. So you recognize here these three combinations I highlighted before. They just come from applying the Liouville vector field to the log of F0. But there are some coefficients in front of them, and those are the transport coefficients. So kappa, for example, that's the thermal conductivity. Eta here is what is called the shear viscosity, because it couples to the shear. And this mu is actually related to the bulk viscosity. I don't know if I wrote this down. No, sorry. Yeah, this is related to bulk viscosity. Now, these coefficients, in principle, you can compute because this all comes from this kinetic theory from the Boltzmann equations. In principle, you know, I mean, it doesn't just give you the structure, but you can also compute, in principle, what these coefficients are. And for example, these coefficients, mu is like, you can think of it like a expectation value of the inverse collision operator. So there's this term here, and then this term here, and these are the same. And then, of course, because it's inverse collision operator, so this is the inverse on the orthogonal complement of the kernel. And remember, this was strictly positive. Okay, so actually, all these coefficients, they are strictly positive, which is going to be important for the third lecture. Okay, so the basic expectation values of the inverse collision operator. In some cases, you can even compute this explicitly. So as I give you an example here for the transport coefficient for hard spheres. So this is when the differential cross section is constant. Then you can compute those. So this is a bulk viscosity, shear viscosity, and thermal conductivity. You can compute them again in terms of this Bessel, modified Bessel functions. and they look, so we can plot them with respect to the temperature. And then courtesy of my colleague, Ana Laura Garcia. And here the interesting things are the bulk viscosity, you see, it goes to 0. I mean, you can show this just by looking at this expression. It goes to 0 in the non-relativistic limit, so if the temperature is very low, but also in the high temperature limits. So the bulk viscosity is an effect that you would only see like I mean, in this intermediate region, and in the if you have a simple gas, then in the non-relativistic case, you don't see this effect is not there. So this was discovered by Israel, that this is a relativistic effect. Mm-hmm. All right, so now for the theory, for the fluid theory to be physically sound in the way I defined in the introduction yesterday, so to be hyperbolic and stable, we need to make at least one generalization of this Chapman-Enskog method. So this Chapman-Enskog method, there are two variants to it, or two generalization, two ways you can generalize it. And the first one I will not go into that, but you remember I explained to you this problem, I mean, with the choice of the frame, which is how you get a non-equilibrium distribution function. How do you associate to it a temperature parameter, a particle density, and a for velocity? And this is non-unique. So we fixed this freedom by asking that the first 5 moments coincide. But if you prefer to work in a different frame, then you could do this by just, when you have this implicit equation for H epsilon, then you could add here an element of the kernel. So this is allowed. And what this would produce for you is now to get a fluid theory in a different frame. So you have this freedom here. Now, more important for what you're going to do tomorrow is, if you go back to the original Boltzmann equation, okay, then we will use a trick where you add 0 to the right-hand side. So this is a 0 because if you look, this only depends on the divergence of J and the divergence of T mu nu. And I told you before, this is imposed at the end to be exactly 0. And then you just think about how you could add this without I mean, by preserving the fact that the right-hand side should be orthogonal to the kernel. So this is why you put the projector here. And then this is one way of writing it, but you see you have here 3 coefficients. So you have here dimensionless coefficient gamma 0, gamma 1, and gamma 2. So this is something you're allowed to add to because it is 0 at the end. However, the difference will be is once you truncate the theory, then it will make a difference. And I'm going to show you, I still have a few minutes to show you how it will impact the theory at first order, okay? And this actually, how you choose this coefficient will actually impact if the system at the end is hyperbolic or not, or if it's causal, it has causal propagation or not. Okay, and so the conclusion of today's lecture, so the first order equations we get, here I wrote them again. So you have the Euler part here. Okay, and this is, if you look at it, this is first order in the gradient. So that's why I put it is proportional to the wave vector k, say. Okay, and then you have these dissipative terms which depend on this correction E1, P1, and Q mu, and P, and pi 1, okay? So these are the dissipative terms, and they're actually of the order of epsilon k squared, okay? So within the, of course, within the Chapman-Enskog, I mean, within the hydrodynamic approximation, epsilon k is much smaller than 1, so that's okay. So these are correction terms. And now, what you obtained from solving the first order equation are these what are called the constitutive relations. So E1, Q1, and P1 are given by this expression with the transport coefficients I mentioned before. Okay, and now if you look at it, this is also of order k. And now what happens if you use this modified, I mean, this variant of the Chapman-Enskog approximation, where you add it here, 0 here, then it will turn out this will add some terms here that depends on gamma 1 and gamma 2. So it will look like this. And within the regime of approximation of the hydrodynamic approximation, these are actually lower the terms. So you don't modify the physical content of your theory. Okay, but these 2 parameters, gamma 1 and gamma 2, they will be important both to achieve hyperbolicity and stability of the equilibrium state. Now, the hyperbolicity aspects, of course, they are related to very large k. So of course, so at the end, what will happen, you will be only interested in the small k results of your theory. But if you want to make any predictions, say solve these equations, then of course you need to have the Cauchy evolution in the control. So you need to control all k's. So you can look at this like a trick of fixing the high k regime of your theory. Okay, so the key question now, and this is going to be addressed in the next lecture, is if this system, this evolution system, as an evolution system, if this has a well-posed Cauchy formulation, and with causal propagation, and if like equilibrium, global equilibrium Minkowski spacetime are at least linearly stable. Okay, so I'm going to address this in the last lecture.